Okay, this video is going to be about carbon and the molecular diversity of life. We're going to start into the basic concepts of organic chemistry. We're going to talk about hydrocarbons and functional groups. Okay, carbon is a very special element when it comes to um, This video is going to talk about carbon and the molecular diversity of life. It's going to focus a little bit on the basics of organic chemistry and also hydrocarbons, putting carbon together with hydrogen, and some of the functional groups that are really important in creating different types of molecules. Okay, to start out, what we must know, the properties of carbon that make it so important. And so we're going to start off with the importance of it and a little definition of organic chemistry, which is the branch of chemistry that specializes in the study of carbon. So carbon is so special that it has its own chemistry course. Organic compounds contain carbon. So when we talk about organic compounds, you should always think carbon. Now, when we think of elements of life, I want you to think of the word sponge. And actually, sponge is not a word. But when we talk about sponge, which is right here, that's sulfur, phosphorus, oxygen, nitrogen, carbon, and hydrogen. And these are the 6 elements that organisms are primarily made out of. Now, carbon can form large, complex, and diverse molecules. That's why it's so special. The molecules of life are all long chains of carbon put together. So when we start talking about carbohydrates and proteins and lipids and nucleic acids like DNA, we're talking about, in at least 3 of those cases, very long chains of carbon that create special properties. So they have emergent properties as you attach different things to them. So when we look at this, all the black, that would be right here, this black chain right in the middle, those are all carbons. The white are hydrogens, and the red are oxygens. So these are carbon, hydrogen, and oxygen are what we're going to primarily be focused on. Now, key to carbon, it has 4 valence electrons. Now, those 4 valence electrons are going to allow it to make 4 bonds. And those 4 bonds are going to allow carbon to make a single bond, a double bond, a triple bond, or it can bond not only to itself, but 4 other things, which makes it what's called, it has a tetravalence, 4 valence electrons, which allow it to bond 4 times. So it forms up to 4 of those covalent bonds. And if we're looking at carbon right here, we have the 6 protons and 6 neutrons, but then we have our first level holding 2, that's full, and then we have our 4 electrons going around the outside. That's our valence. Now, typically, it's going to bond with hydrogen, oxygen, and nitrogen. Remember the sponge, HON, but it can bond with other things as well, like phosphorus or sulfur or many other things. So this right here is the most basic of all organic compounds, that the C with 4 hydrogens attached to it. See, here's 1 carbon with 4 things attached to it, and that's called methane. And methane is one of the simplest hydrocarbons. Now, we get into the diversity of carbon, and we can have bonds that can be single, double, or triple covalent bonds. So right here, I see all single bonds. Look at that. That is a double bond, and that is a triple bond. Now, the interesting thing about that is its ending. If they're all single bonds, we call it an alkane, and that ends in ane. If there's a double bond in there, we call it an alkene, And there's the ene, ethene. And if there's a triple bond, we call it alkyne. That's an alkyne. And we would call this ethyne. Now, the reason this is called ethane, ethene, ethyne, is because there's two carbons. And if there's two carbons, that's always going to be an eth prefix. It's only the suffix that's going to change as we have different bonds, doubles and triple bonds. So here are some examples of typical alkanes. And when we say alkanes, what we're talking about is all single bonds, and therefore it's saturated with hydrogen. And the saturation is a really important word to use, and we're going to get into that later when we talk about saturated and unsaturated fats. I'm going to draw a couple things here. Right here, methane, CH4. Okay. Now I'm also going to draw, just clear that out here. I'm going to draw ethane, C2, and then off of each one of these is going to be a hydrogen. So H. I know this is not my best work, but just bear with me. Okay, so that's ethane. So that would be this one. C2H6. Prop. Well, if we're doing propane, now all I have to do is add my hydrogens. C3, H1, 2, 3, 4, 5, 6, 7, 8. C3H8. So all of these are basically the same principle as you're adding all of these. The key is this. What you'll notice is meth, eth, prop, and bute. These are the first four prefixes of the hydrocarbons. Meth means one carbon, eth means two carbons, prop means three carbons, bute means four carbons, and look what happens afterwards. Afterwards, you get into pent, 5, hex 6, hept 7, oct 8, non 9, dec 10. Now we're getting into those typical prefixes that actually mean that number. Those first four, though, meth, eth, prop, bute, you just got to memorize those. Okay, let's move on. All right, so when we get into hydrocarbon models, this is what we've been using right here. This is the Lewis dot form. So Lewis dot is simply the carbons put together there with the hydrogens around the outside like we did before. But we can simplify that into a condensed form. And if you notice that right here, here's a CH3. Well, that is actually right there, CH3. And this CH3 is actually right there. But look at this one. That's a CH2, CH2. Another CH2, CH2, CH2. You can even simplify that and take these bonds out and just squish it together like that. You get the same thing. That would just be the carbon skeleton. We just left out the hydrogens. But this is probably my favorite right here, called the line form. And the line form, what it does, it says forget everything. We're taking everything out. But here's how you read it. At the end is a carbon. And anywhere you see an angle is a carbon. So 1, 2, 3, 4, 5, 6. That's the same as this one. 1, 2, 3, 4, 5, 6. So this one would correspond to here. This one would correspond to here. I'm going to make this a lot better. That one is right there. That one is right there at that corner. That one is right there. That one is down here. This one is here. And this one is here. And these are the bonds in between right there. That's a bond, 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 bond. All right. Now, another thing you should think about is at the end there's a carbon, but right here we should also see 3 hydrogens. We should see 3 hydrogens here. There's H3 there. That's a CH3 there. That's a CH3 there. I wonder what would be right here. Well, right there would be a CH2. That's a CH2. Now at this point, we're going to jump to what we were looking at earlier in the year. That would be the functional groups. Now, the basic functional groups are hydroxyl, carbonyl, carboxyl, amino, sulfhydryl, phosphate, and methyl. Now, what happens is when you stick these on to carbon skeletons, they end up changing the function of that or change the properties of that hydrocarbon. So these functional groups actually give them different functions. So functional groups, molecular components attached to the carbon skeleton are mostly involved in chemical reactions, and they give the molecule a particular set of characteristics. The first one is hydroxyl. That's the OH group right here. Now, hydroxyl is very common when we start talking about alcohol type groups and as well as sugars. So you're going to see an OH group in things like ethanol, propanol, methanol. Those are all alcohol type compounds, alcohol compounds, and sugars like glucose and sucrose and fructose and lactose and maltose. Those are all sugars, and they will have the OH group on there. You're going to notice this right here. That's the bond. It will attach to the carbon skeleton at that point. So the oxygen is what attaches. Carbonyl is a double bonded carbon right here to an oxygen. Carbon double bonded to an oxygen. And we can form 2 types. They're keto groups and aldehyde groups. That's a little bit specific, but you should just be aware that that's the type of molecule that you have here. And a carbonyl is just a carbon with a double bonded oxygen. Now, you don't want to get that mixed up with our next one, which is a carboxyl. So you have a carbonyl and you have a carboxyl. Now, the carboxyl you're going to see in the amino acids, which we're going to talk about when we talk about proteins. Carboxyls are a carbon double bonded to an oxygen. That's kind of like that carbonyl, but now we took a hydroxyl and also attached it to the carbon. So we have a double bonded carbon here to an oxygen, and then a hydroxyl as well. Now, this is special, and they can form acids, because if you notice, this has come off into solution, and anytime we increase the concentration of hydrogen ions, remember, we are creating acids. So carboxyl groups can act as acids. Amino group. We've heard this term in amino acids, and yes, we will find these in amino acids. And anytime you see amino, you're dealing with a nitrogen. And a nitrogen is going to be bonded to a hydrogen here and a hydrogen here, and sometimes a hydrogen here, right there. As you can see, it goes back and forth between NH3 plus with an NH2 and an H plus. what's interesting about this is you can take this out of solution. And if you're taking hydrogens out of solution, it acts as a base. So you have an amino acid where one can take the hydrogen ion of the other. And amino acids have an amino group and a carboxyl group with a couple other things on there, but we'll talk about that when we get to proteins. Phosphate. A phosphate is a PO4. P double bonded to an oxygen and 3 other oxygens, PO4. Now, a PO4, you see phosphates a lot in, DNA, sugar phosphate backbone, as well as in ATP, DNA and ATP. So those are 2 molecules that we will talk about a lot, and we should know that there are phosphates in there. Sulfhydryl. Sulfur is involved here. Sulfhydryl, there's where that sulfur is. It's basically just a sulfur attached to a hydrogen. And this sulfhydryl group is typically found in protein structure. Very important in protein structure. Now, this last one is a methyl group, and we've seen this. Hey, look at this. Whoops. CH4. Well, that's a CH3. Well, what we did was we took a hydrogen off, and we allowed this bond right there to attach to something else. So when you attach that onto something, you are methylating that molecule. And so it can affect the shape and function of other molecules. Methylation is ways that DNA can be silenced, turned on, and turned off through methylation. We'll get to that when we get into DNA. Okay, so here's a quick recap of those functional groups: hydroxyl, carbonyl, carboxyl, amino, sulfhydryl, phosphate, and methyl, if you want to look at those. And here's a chart at the very end to help us kind of connect a few things. Now, really what we're focused on here is where do you find them most often? For example, hydroxyl and sugars and alcohols. Carbonyl, you're going to find those typically in ketones and aldehydes. We'll get more of that later. Carboxyl is the carboxylic acids, and amino with the amines. Both of those are found in amino acids. Sulfhydryl are found in proteins, phosphate, DNA, and ATP, and methyl groups. You can find them a lot of different places, anything with a methylated compound inside of them. So if you have any questions about this, please ask in class.